Okay, so now that we saw what, let me move this around. Now that we saw what 2D motion is, let's jump right into what equations we'll be using. Okay, so remember that the problem with 2D motion is to, well, not the problem, but the trick of 2D motion is to break it down into two types of one-dimensional movements. So we can break it down to the horizontal motion, and we can break it down to its vertical motion. Vertical. So we know that the horizontal motion is movimiento rectilíneo uniforme, so uniform straight line motion, and vertical is movimiento rectilíneo uniformemente acelerado. This means that acceleration in this type of movement is zero, and here acceleration is constant. Okay? One thing that you need to really understand about this type of motion is that my horizontal velocities or horizontal components, so displacement in the horizontal direction, acceleration in the horizontal direction, which in this case is equals to zero. These things, let me put this, let me mute my computer because, okay, there we go. So these things will not affect the vertical components. Okay. So my horizontal data, my horizontal vectors, so velocity, position, and acceleration, these vectors will not affect in any way these vertical vectors, and vice versa. These won't affect these ones. Okay. So there is no effect on these. Okay. So no effect. No effect of the horizontal on the vertical, and no effect of the vertical on the horizontal. Okay. Uh, Here, let me see what else we have to say. Oh, also, these equations, like I said in the past video, are ideal. And they are ideal because we are not taking into consideration air resistance or air drag. If we wanted to take into consideration air resistance, we would have to go into a very beautiful field of mathematics, but probably out of your curriculum, called differential equations. Okay, so it is possible to take into consideration air drag into our kinematics, right? But that would have to take into that would be through differential equations, and we are not quite ready to work with those. So we'll keep with the simple stuff. So we will continue looking at this, no air drag. Okay, the only force that acts on our movement is gravity. Okay, so our only acceleration will be in the y direction, and it's constant at 9.81 meters per second squared. Okay, uh, so let's break down, as I told you, let's break down our problem into two different problems. So first we'll look at the horizontal problem. So let's look at our horizontal movement, horizontal, horizontal movement equations. So let's look at our horizontal movement equations, and let's remember that these equations, the only thing that's different from our vertical equations is that, hey, pivo, cállate, ven para acá, ven para acá. Sorry about that. My dog is getting a little bit crazy. Stop it. So our horizontal movement equations, let's see. are the same ones that we'll be using for the vertical movement, but in this case our acceleration will be 0. Okay, so since there is nothing that is accelerating my projectile in the horizontal direction, this is going to be always true. Okay, since there is nothing that is accelerating or decelerating my projectile in the horizontal direction, my velocity in the x direction will always be equal to my original velocity in the x direction. Why? Because it's not being accelerated and it's not being decelerated. Uh, Another thing that we need to take into consideration is this. So this will be our first equation. Our second equation, uh, we'll get it from something that we already know. So 1/2 ax t squared plus vox times t plus x0. Since ax is equal to 0, all of this gets canceled out, and we are left with x equals vox, so my original velocity in the x direction, times t plus x0. So this is the equation that we'll be using. Okay. Okay, that's equation number 2. Or remember that delta, whatever, is final quantity minus initial. So my change in position, my delta x, will be my final position minus my initial position. So this thing can be rewritten as delta x equals vox times t, and that is it. And finally, no, that's it. That's it. These are the two equations that we'll be using for our horizontal movement. Okay, they are very, very simple, and they are exactly the same equations that we use for vertical movement, but in this case, since acceleration is 0, this thing cancels out. For our vertical motion, uh, let me create a new layer. So for vertical movement, we already have the equations we need. And we had these in the past video, so I'm just going to write them down. Vy is equal to the original, the initial velocity in the y direction, plus my acceleration in the y direction times t, or this can be rewritten as delta v equals ay times t. Let's call this 1. 2, our famous position equation, y is equal to 1/2 at squared, a y direction, plus voy times t plus y0, or delta y equals 1/2 ay t squared plus voy t. And let's look at these other two equations. Delta y can also be written as vy plus voy times t. So the average velocity times t. And my fourth equation can be written as vy squared is equal to voy squared plus 2ay delta y. So these two equations, these two movements can be, okay, so this one and this one, oh, sorry. So these two type of movements are basically the same equations, just that in one case my acceleration is 0, and on the other case my acceleration is constant. So for this, acceleration is equal to 9.81 meters per second squared. It can be negative depending on your frame of reference. Uh, and remember that in order for us to break down the problem into 2 dimensions, we need to take into consideration that our velocity vector can be broken down into Vx and Vy. And that is it. So thank you guys for paying attention. And the next video will be of us actually putting these things into practice. Thank you. Bye.